The PLCprofessor.com website and PLC Professor channel on YouTube presents RSLogix5000, a jump start with ControlLogix. We just posted one on our YouTube channel for CompactLogix. They are very similar. However, I'm going to elaborate on some of the major differences between the ControlLogix and CompactLogix as I'm showing you how to create a project with ControlLogix. If this is your first video that you're watching on programmable logic controllers, you're in the wrong spot. On my channel, PLC Professor YouTube channel, there are between 60 and 70 training videos. You need to go to the series on lectures. Actually, you can start with Introduction to PLC, Part 1 and Part 2, and then there's many other presentations labeled lectures, 0, 1, 2, 3, all the way to, I think, to 11 or 12 that cover basics of PLCs, because this does not. This simply shows you how to use RSLogix5000 as a tool to program a ControlLogix processor. So we're going to go through, we're going to create a project and then explain a few things along the way, but it won't cover the basics of a PLC. So we're going to start out by going up to File. So right now we have RSLogix5000 open, but we have no file open, no project open. So we want to go create a project, so we go to File, New, and for this is ControlLogix, so we're going to go up and pick, we'll pick an L75, and it's going to be version 20, revision 20. That means the firmware in the L75 processor has to be flashed to 20, and so we're going to write our program with version 20. With each new revision level of RSLogix5000, more features are supported. Now remember that not only does the processor have to have a firmware level that matches the revision level of this software. So your processor has to be flashed to firmware level 20, revision 20, and then you have to program it with revision 20. There are many modules. As a matter of fact, most of the I/O modules and communications modules, they are smart in their own stead, meaning that they have a RISC processor, their own RAM, and their own firmware. So you have to be conscious of the firmware level of these modules. Now, a good way to do that is to open up RSLinks and browse through your driver, open up the properties on each module that shows up in the backplane in the chassis, and write down the revision level. That way, when you're configuring your project, you can do it properly. So we're going to give this a name, and we'll just call it something clever like my CLX, my ControlLogix, and we're going to put it in slot 1. Now the processor for CompactLogix is always in a fixed location, but for ControlLogix, you can put the processor in any slot that you want. You can put more than one processor in the chassis. You could put a processor in every slot if that's what you wanted to do. I cannot think of a good reason to do that. 2 processors, I can easily support a situation for that where you want to share the, I guess you'd call it the code execution bandwidth, but we're going to stick to 1 processor. Okay, so all we've done so far, folks, is File, New Project, and we selected an L75, revision 20, and we gave it a name. That's all we've done. So let's click OK here. And in the meantime, the geeks in the background are going to be putting together your package, and it will suddenly appear in the controller organizer. So everything you see to the left was created by RSLogix5000. Now some of these folders are empty, and some of them may have something in them, but they're undeveloped. Now, for those of you that are accustomed to using RSLogix500, and this is your first venture into 5000, let's open up RSLogix5000 and make it about the same size as our 5000 so we can jump back and forth to make comparisons. So I will just stretch this bad boy down here so it's about the same size. Now we'll create a project in 500. File, New, and we'll pick this bad boy right here, 64K of RAM, version 10 or later, firmware revision 10 or level series C. So that's the biggest and best processor that RSLogix5000 programs, the SLC 505 Ethernet version with 64K of RAM. Now I want to point out something. You may think that the ControlLogix and CompactLogix has a whole lot more RAM than a SLC 500, and it does. However, it takes 20 times, that's 20 times the RAM to do in a ControlLogix what you did in a SLC 500. So whatever the RAM is in your ControlLogix, divide it by 20, then compare that to what you were doing in a SLC 500 or a 580E PLC5. Okay, so first thing I want to point out is I'm going to collapse the controller properties here, and I want to point out the program files and the data files. The rest of it we're unconcerned about. In a SLC 500 there is only one program, so the program files are right there, and you see you have ladder 2. Ladder 2 is a given. You can add more program files by right-clicking, New, and we'll let that be ladder 3, and we'll call it setup, just to give it a name. No description. Okay? So you can create many more routines in this program, but a SLC 500 only has one program. Now, if we jump back to 5000 and go to the same spot, we have a program and we have a main routine. That would be ladder 2. And we could rename that ladder 2 if we wanted to. We'll leave it main routine. And you see the little symbol right there? It looks like a ladder, and then it's got a little sheet of paper on it. That means it is the main routine. Because as you remember, in 500 land, only ladder 2 executes automatically when you go into the run mode. If you want to execute ladder 3, you have to put something in ladder 2 like a JSR to ladder file 3 to run ladder file 3. So ladder 2 is the main routine in a SLC 500, whereas in ControlLogix or CompactLogix, this is the standard default format, and you get a main routine of the main program. But notice that in 500, program files, that was under the main folder under project. It wasn't, program files was not a subfolder. In 5000, this program is a subfolder of the main task. And if you look close at the folder for main task, you see a little clockwise swirly. That means that it is the continuous task. All the Logix engine processors, that's ControlLogix, CompactLogix, FlexLogix, DriveLogix, and SoftLogix, they all allow you to have multiple routines, just like SLC 500, in a program, but the Logix engine steps it up from there and allows you to have multiple programs with multiple routines. As a matter of fact, the multiple programs fall under a task, and they allow you to have multiple tasks. So listen very carefully. Right there it shows main task. I can create 31 more tasks. Only one of them can be continuous. There's periodic task, event task, and we'll leave it at that for right now. So you can create 31 more tasks, and each of those tasks can have multiple programs. How many programs, you ask? Each task can have 100 programs. So that's 32 tasks, each with 100 programs, each with the number of subroutines only limited by how much memory you have to create them in. So a ControlLogix processor has the, we'll call it the program granularity of 3200 SLC 500s or MicroLogix. Now, you wouldn't do that. I can't see an instance where you would create something that convoluted. Nonetheless, they give you the organizational capability and isolation of both the program files and the data files. So if we jump back to RSLogix5000, here's your data files. You've got one set of data files. And notice they're in numerical order: 0, 1, 2, 3, 4, 5, 6, 7, 8. Output, input, status, binary, timer, counter, control, integer, and floating point. But these data files right here, both your I/O, remember these memory locations right here, like for I1 input, those memory locations are continuously updated by this status of the inputs on your input module. Of course, the processor has to drop whatever it's doing and go out and collect those one card at a time. So the SLC 500 or the RSLogix 500 family cannot chew gum and walk at the same time. They have to stop, chew the gum, stop chewing, and then walk some. So they cannot execute program files and deal with the I/O simultaneously. And of course, the controller, through the ladder files, controls these bits, these memory locations, which eventually get sent out to the output cards. And now status, if you ever worked with the status files in a SLC 500, you see you have first pass bit, you have some information on the processor, scan times, selectable timed interrupts, etc. Okay, these are accessible in the SLC 500. They are not accessible as a graphical user interface in ControlLogix. You can write program code using them, but you have to use a GSV to get the system variable, to look at it, and then you have to use an SSV to write to it or to set it. Set system variable, get system variable. A little more work to work with the status files, but it can be done. Let's not worry about that right now. And then, of course, in SLC 500, you got binary. And remember that this is actually a pre-declared variable, because in RSLogix 500, all of your variables are pre-declared. In a sense, they give you one element of the array B3. This is the first element, element 0, of array B3. Here we have an array, but it's a single element array, but it can be expanded out to 256 elements, a maximum of. How do you do that? You go to properties, and then you put in how many elements you want, up to 256. Now, if I were to do that, I would have a data file B3, element 0 through 255. That's 256 elements. I won't do that. I'll just give it 10. So it's something easy to look at. Apply, okay. Now look, I have 10 elements. I have B30, B31, B32, etc. Okay? Now, let's go to timers. Here I have one timer. And if I had a symbol or description, it would appear right there. This is also a pre-declared variable. So T4 is the tag name. But it's an array of timers. This is the first element, element 0 of timer array 4. If I want to expand this array to be more than one element, I just go in and put how many elements I want in there. I want 5 elements. Now look, I've got timer, I got T4. That's the tag name. It's a 5-element array, element 0 through 4. That's 5 elements. But the tag name is T4:0, T4:1. Those are tag names. They are not memory locations. And what you're looking at right here is a data type. Okay, in ControlLogix, they have many data types. As a matter of fact, we'll just open that up. So here we have predefined data types. I'm going to click on this. If you haven't seen this before, don't be overwhelmed. Okay, try to keep this in perspective. So I'm going to click on this, and I'm going to point out something. See that right there? That BOOL, Boolean. That means a bit. That is a data type. ControlLogix or RSLogix5000 calls these atomic data types. I mean, they're like atoms. that make up molecules, okay? So Boolean is 1. Double integer is 1. That's 32 bits. And we have integer. That's 16 bits. That's basically what SLIC500 used, was 16-bit integers. And then we've also got single integer right there. And there's also string, wherever it's hiding. I know it's in here somewhere. ST. String. Yeah, when you know it's hiding from me. Well, it's in there someplace. Okay. So those are the atomic data types. Boolean, single integer, integer and double integer, and then there's real. I missed that one. That's the one I was actually thinking of, was real, R-E-A-L, right there. That's floating point. So in SLIC500 that was called floating point. Here it's called real. So those atomic data types make up all the rest of these. So let's pick timer. You're familiar with a timer. We'll open that up. Now these are templates, okay? These are data types. So there are so many different data types available in RSLogix5000 that they actually have this little library here for you to look at. So when you create a tag, you can assign it to any one of these data types. Now most of these are meant to support an instruction, especially in function block diagrams. But look over here, timer. Now notice this is all grayed out. You can't change this, but you can look at it to your heart's content. There's the preset, the accumulate, the enable, the timer timing, and the done bit. If we go back to 5000, there you go. There's the enable, timer timing, done, the preset, and accumulate. Now, the SLIC500 MicroLogix, that family, has multiple time bases. Some of them have 1 second and 1/10 of a second, like you see here. Others have 1 second, 1/10 of a second, and 1/1000th of a second. So in ControlLogix and CompactLogix, all timers have one time base, 1/1000th of a second. Now see, that makes a lot of sense, because if you had, no matter what you want, if you want 100 seconds, that's 100,000 units. Now remember, timers and counters both count. Counters count events. Timers count units of time. Okay, so there's a data type that you recognize, timer. We'll cancel that one. We could go up here and pick counter. See, preset, accumulate, count up bit, count down bit, done, overflow, and underflow. So you recognize some of these predefined data types. We're going to collapse this, okay? You also have user-defined data types. You can create your own data type. And that is very clever. We're not going to stop and do that right now, because we're getting a little ahead of ourselves. There's also module-defined data types. With SLIC500 MicroLogix, with MicroLogix, some of it was predefined. You got a fixed number of words for inputs and outputs. With SLIC500 and other MicroLogix, as you added I/O modules, you had to go add those I/O modules into your project. And when you did that, you didn't realize it, but you were adding a data type that defines each of those modules. In other words, each module can be represented by a data structure. It's either integers and reals, or some combination thereof. So if it was one of those specialty modules where you have to set up a configuration file that you write to the module when it first goes into the run mode, and then it works very fine from there on, and you just get the information to and from. So each module has a data structure. Now the data structure for some of the modules we're going to be looking at are quite different, as you'll see. Okay, so we're creating our hardware image. And so far we have a 10-slot chassis, and in slot 1 we have a L75 processor. We have one program and one routine. I'm going to double click on this, and you'll see that it's empty, but it does automatically give you a fresh, new, unfinished rung if you open an empty program routine. I'm going to delete that. And we'll just hit this X right here, gets rid of whatever's here. If you hit this X, you get rid of your controller organizer. You don't want to do that. We will shrink this down a little bit though. Okay, there's some more explaining that could be done with, well, I will explain one more thing. Now, remember I told you you could have you can have 100 programs in a task. Notice that each program has its own program tags. So if we back up to 500, all of these tags belong to that one program, including the I/O. So when we go to 5,000, now we got a situation where we have I/O that we're going to add down here, but who does the I/O belong to? It belongs to everybody. So under controller tags, you will always find all data types, data structures that belong to the outside world, outside the connector on the back of the processor. So any I/O modules, any communications that goes on, that comes in and out of the back connector on the back plane on the processor, that's always going to be in the controller tags. However, your program tags are only available to this program. So if I go into the main task and I create a new program, and we'll call it something real clever, like Monkey Shines, and we're going to schedule that in the main task. Oh, looky there. Now we got two programs. Now we don't have a main routine in this one because that's not part of the default assignment, but I can give it one. I can right click, new routine, and I can call it the main routine. How original is that? Okay, and I could pick any language I want. Structured text, function block diagrams, sequential function charts. We'll stick to ladder diagram. Okay, because this lecture is primarily to folks that are moving over from the RSLogix5000 family to RSLogix5000. So I'm going to click OK. Now look, these two look identical, don't they? However, these program tags, in other words, these data files right here, are only accessible to this program. These data files, program tags, are only accessible to this program. So this is analogous to a SLC 500, and this is analogous to a SLC 500. So what you have here is the structure of two independent SLC 500s, each with its own tag database. However, they don't have separate I/O. So, and you'll see in a minute, when you add I/O cards modules on a 1756 backplane or wherever they're at out there, you have to add each one individually and configure it, because with this product, you cannot assume that the processor owns everything out there that is accessible. You have to tell the processor, as part of its hardware image, what belongs to it. So we're going to pause for a second here. We're almost up to 25 minutes. I think we'll come back and add an I/O card or two and then continue on. Okay, let's add some I/O cards to our project. First, let's jump over to 500 and refresh your memory how you added I/O modules in RSLogix5000. You went to I/O configuration, you double-clicked, you picked your chassis. We'll make it a 10-slot rack. Okay, now so you got 0 through 9, but slot 0, of course, is occupied by the processor, always. In SLC 500, the processor occupies slot 0. That gives us 9 slots for I/O. Now, if we were online with our SLC 500, we could click this button, read I/O config. It would go out and populate all the slots in our hardware image here that have an I/O module. But instead, what I'm going to do is I'm going to go pick, let's see, I want an OB16 right there. So I'm going to double click on that. See, there's one in there now. And I'm going to go get an IB or an IV, one or the other. We'll get a fast IB16, okay? Now we got two cards we just added. Now one thing I didn't show you, you know what? I'm going to delete that and go back over here to output. Yeah, it's too late. It already got added, evidently. Yep, I would have to delete. Now go back here to output. No data exists for this file. Input, no data exists for this file. So in SLUG 500, output file and input file really didn't exist until you actually added I/O modules. And it's the same thing in ControlLogix. So now let's go back to I/O configuration, and I'll redo that very quickly. I had an output card, an OB16, and then I put in an IB16. It was a fast one, but this is good. So I'm going to close that down. Now I'm going to go back, double click on output. Look, there's my 16-bit card. Go to input, there's my 16-bit card. Now I want you to remember that that's all that there is associated with an input and output card in SLUG 500. So we go to ControlLogix, and we're going to scroll this down. As a matter of fact, I'm going to collapse this for the time being. Now remember, you understand that the controller tags is where you have your I/O, and you see there's nothing in there right now. Program tags is where you have tags that are unique to this program. And then we have another set of program tags for monkey shines. See right up there? Scope, monkey shines. So we can have processor, main program, or monkey shines. Those are all this tag scopes, meaning who can use those tags. Okay. So I'm going to collapse the task just to give us more space down here. Now I want to add an I/O card. So I have to right click on the backplane, new module, and I happen to know that I want an OB16. So this is type forward or type ahead. So up there where the cursor is, I'm going to type in OB. Now you notice all the part numbers are 1756 to begin with. That's because it knows this is a 1756. So the software is intuitive. It's not going to bring up every known part number with an OB in it. Well, I'm going to take and give you the best output card there is, and that's the OB16D. That's the diagnostic version. That's the Big Daddy, or D for Big Daddy. BD, Big Daddy. OB16D, diagnostic. So I'll double click on that. Now here's where you got to start being careful. We'll just leave it 3. So the major rev level, firmware level for that card, because remember, this OB16D has its own microprocessor in it, has its own RAM, and has its own firmware. It is a computer in its own right. So in SLUG 500, every module on the backplane was dumb as a brick on the backplane. And there was no communications across the backplane. Now there's this rare instance where you can steal the backplane called pass-through, and you can pass communications through the processor across the backplane and out a port on the front of a module. But everybody on the backplane is dumb as a brick except for the processor. On a 1756 backplane, it's called a passive backplane, everybody is smart. Everybody communicates. Where in a SLUG 500, the processor turned on the modules one at a time to collect inputs, executed the program, and then went back and turned on the output cards one at a time to give it its update. In other words, it had to drop everything it was doing, collect the inputs, then it ran its logic, dropped what it was doing, and sent out the outputs, and then went back to running logic. With 1756 chassis, it's a passive backplane. Everybody on the backplane is a node on a 32-bit parallel network. Now, if you haven't heard this before, just let that sink in, which means the input modules don't get turned on by the processor. The processor tells them when they first come into contact, I want you to come and update my memory with your status every 20 milliseconds. And oh, by the way, input 6 is very special to me. If it changes state, I want to know right now. And oh, by the way, it's a 32-bit parallel backplane, so it takes you just as long to send one bit as 16 bits. So just if number 6 changes state, update my memory right now with everything. Okay, so here's our output card, OB16D. We got to give it a name. Remember, everybody communicates on the backplane of a ControlLogix chassis. So everybody has to have a name. So we'll just call this DC outputs. And I usually put the slot number after it, just in case I see this tag someplace. I know it's in slot 0. Of course, slot 0 is already picked. We want full diagnostics output data. But I'm going to disable the keying here. If I pick compatible, then the 3 has to match the module out there. If I pick exact match, then the 3 and the 1 have to match. In other words, the major rev and the minor rev have to match between my program and the actual hardware out there. So I'm going to select disable keying, which means that any 1756 OB16D will do, even if it's not the right firmware revision level. And I'm going to click on Open Module Properties here. Say OK. Wow, look at this. Module Properties report for this guy right here. See, we've got him added here. Oh, and check this out. Remember that there were no module-defined tags? There was no plus sign there when we started. Now we've got 3 new data types. These are module-defined data types. So it takes these 3 module data types in order to incorporate this card into our hardware image. So we'll ignore that for right now. We'll get back to that later. So first thing we want to do is pick a requested packet interval, RPI. And you're thinking, no, hold on now. This is an output card. The processor is updating this output card with the state that its output should be. But this card actually sends data back to the processor on a regular basis. We'll see what that data is here shortly. You can also inhibit this module temporarily while you're commissioning your project. Let's say that this module is not quite right and you want to inhibit it, so it's there, but it's as if it's not there. You check that box. If you want a major fault on the controller, if the connection fails between this module and the processor in the run mode, then you check that. Okay, now we'll look at module info. This is the info of the actual hardware module. We don't have any hardware. This is a hardware image. Okay, we don't actually have any hardware yet. So you won't see anything here until you go online. Then here's configuration. Look at all this stuff. My goodness. What do you want the outputs to do during the program mode and the fault mode? Do you want them, during the program mode, do you want them on, off, or hold the last state? In the fault mode, on, off, or hold the last state by individual point, 0 through 15. Okay, output verify and no load. Think about these two, output verify and no load. You know what this is doing? You know, the output card that we're talking about is a computer, a little mini computer, no hard drive, no screen, no keyboard. But it's got a CPU, it's got firmware, and it's got RAM. So it is actually monitoring the current on the field side of the wiring on the face of the module. So it can watch the current flow in the field. So if that field device is a solenoid, it actually sees the current increase when you turn on that output. That's how it can tell you output verify and no load. So if you have this checked, remember I said that this had an RPI, we set it at 20 milliseconds. So every 20 milliseconds, this is the data that gets sent back right here. Output verify, it actually verifies, when you told the output to go on, it verifies that the current actually increased in the output circuitry. And of course, if there's no load, in other words, let's say you have it's a solid state output device, so there's leakage current. So if you have an open wire, you're going to have no load from the beginning. And then you can also enable whether or not you want these faults to latch. But wait, that's not all. Diagnostics. It also has electronic fuse. It automatically opens and turns off the output if the current's too high. Remember, it's monitoring the load current in the output. And here's where you can reset the latch diagnostics if you were actually online with this card. Check this out, pulse test. You can, if you're online, you can click this button and it will send a pulse out to point 0 of that output card just long enough for the current monitoring circuit in the field wiring to see a little pulse of current, but not long enough to actually turn the device on. And then, of course, backplane. This is the communications information, if you want to call it, the live information for communications on the backplane. That's pretty heavy duty. I mean, it's almost like it's a little PLC by itself, but you can't have any logic in it. Okay, that's enough on that. That's an output card. Okay, take a little break, stretch your legs, and we'll add an input card. Well, alrighty then, we added an output card. Now let's add an input card. Once again, we right-click on the backplane, new module, and I happen to know we have an IB16, so we'll type in IB, and we'll pick IB16D. We'll just leave it Major Rev 3, and we'll call it DC underscore inputs. And we're going to put it in slot 2 because our processor's in slot 1. So notice that this little window here, this little field, it knows slot 1 and 0 are already occupied. Otherwise, it would say 0 or 1. So we'll just put in a 2 there. Okay, we want full diagnostics, and we're going to disable the keying. Ordinarily, you might do compatible or exact match in a real project. But we'll just hit disable keying and see that's all grayed out now. Open module properties, and there's our RPI, and it's set at 20 milliseconds. You can make it as low as 0.2 milliseconds, which is 200 microseconds. So you can make it 10 times faster than that. We'll just leave it alone, and you can make it all the way up to 3/4 of a second, 750 milliseconds. You can inhibit the module if you don't want it. If you want it out of the mix right now while you're commissioning the project. And again, you can select a major fault on controller if communication fails when in the run mode. Now, a lot of times you want that. You want a fault if the communication fails between the module and the processor. Module info, exactly as we saw with the output card. This is information that literally comes from a chip in the module, but only when you're online, and you can actually get information from the module. Now we'll do configuration. Now this is an input card. Now you remember I told you that the input card updates the I/O image in the processor's memory on the RPI, requested packet interval, which we have set to 20 milliseconds. However, we've also got change of state set for all of the I/O cards. So if it changes from off to on or on to off, all these cards will immediately update the input image in the processor's memory with all 16 inputs. So we would probably turn those off. And I said input 6. We'll just select that one. You also have an open wire diagnostic. Remember the current monitor in the output card's field wiring? Ditto, same thing here. This module monitors the actual current flow of the input device. Now, what kind of an input device can you imagine where you don't want an open wire fault? That's right, a dry contact. If you just have a push button wired up to an input, it is, and if it's a normally open input, well, every time, the whole time no one's pushing the button, it's open, right? And you really wouldn't want to do it with a normally closed button, because every time you push the button, then you're going to get a open wire diagnostic. So if you have dry contacts, then you want to turn off the ones that are dry contacts. And of course, you don't need to latch them. Okay? Also, you can put a debounce filter in two groups, 0 through 7 and 8 through 15. So for these 8 inputs and for these 8 inputs, you can put in a filter of 1 or 2 milliseconds, and it ignores a change of state unless it's greater than this input filter time. That's kind of like a debounce timer. And you can do it from off to on and on to off in two groups of 8. Okay, diagnostics. Here's where you reset these diagnostics. Okay? And then, of course, backplane. This is the communications information between the input module in slot 2 and the processor in slot 1. So you hit apply and OK, and there's our hardware image. Now if we go up to module define, ooh, look, we've got 5 of these puppies. For the input card, we have DI configuration and input. So if I double click on the configuration, remember the filter off to on and on to off, remember the change of state, fault latch enable, open wire. This is the configuration data type for an input module. Now, it doesn't say IB16 because this data type can be used for more than one type of digital input DC module. See, it just says Allen Bradley 1756, digital input, direct current, DC, diagnostic, configuration. Okay, and so if we close this one and open up this one's not quite as vast. It has fault bits for the inputs. Remember, you can configure it to have certain faults. This is the actual data. So hello folks, right here, the actual data from that input card, this is where it appears. Now notice the data type is a DINT, double integer, 32 bits, and this is a 16-point card. Well, everything's 32 bits. So the first 16 bits of this word are available, and the other 16 are hanging out in the breeze. They're there, but you can't use them. And then coordinated system time timestamp. You can actually collect a timestamp from some of these inputs. And then, of course, open wire. Okay, those are the 2 tags for the input card. For the output card, you have the actual output data. So the first 16 bits of this double integer are the actual bits that control the outputs. This is the diagnostic. Remember, what do you want the outputs to do in the fault mode? What fault value do you want? Program mode, no load, output verify. This is all the configurations. See the C? Okay, we'll close that. And then here's the information that comes back from the output card to the processor every requested packet interval, RPI. The fault 32 bits, the data 32 bits, coordinated system timestamp, fuse blown, no load, output verify fault. So you can actually write code that uses all these tags. Like if you have no load, you can use that bit that comes back from the no load to put a message up on the screen that says that your input device blah 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 on input such and such is open. Or you can say that the output didn't go on. You can halt everything right there, because even though you told the output to go on, the field wiring failed, and you want to stop the process because the output went to a solenoid valve that extended a hydraulic cylinder, and if that hydraulic cylinder doesn't extend, of course, you're probably going to have proxies on the cylinder anyway, so you'll know whether or not it extended. This is just another neat little feature. So we'll cancel that. Okay, there you go, folks. Okay, we've covered multiple programs, and we've covered module-defined data types. We talked a little bit about predefined data types. There's a bunch of them in there. way beyond the scope of this little short lecture. Then there's user-defined data types. What say we just go ahead and do one of them, just for grins, okay? So I'm going to right-click, New Data Type. Oh my. And we will call it vehicle. Okay? And vehicle's generic. Could be truck, car, you name it. So now we're going to create members. Okay? So the first member will be type. Okay? And because there's more than 2 types, you got trucks and cars and buses. There's 3 all by itself. So the data type, we're going to say that it's integer. No, we're going to make it single integer. SINT. Okay? And then let's have length. Width. Height. Color. Weight. Passengers. Storage. So length, because it can be in inches and fractions, we need a real, R-E-A-L. In other words, a floating point. So length could be 197.85 inches. Okay, so the next one, another real for width, another real for height. Color, we could make that an integer, or we could make it a string. Okay, we'll make it a string. That way it can be alphanumeric. Weight, that's going to be a real. Passengers, that's going to be a single integer. And I'm taking that to mean capacity. And storage, that's a Boolean. In other words, storage is yes or no, 1 or 0. Okay? So there, we created our data type. Now we say apply. Okay, now looky here. Under user-defined data type, we got vehicle. We open it up, look what we got. Now notice it's not all grayed out, so you can change it. Now let's go create a tag of the tag type vehicle. But before we do, let's see, we'll go to controller tag. Ooh, look, there's our I/O. There's our 4 data types for slot 0 for the output card, and our 2 data types for slot 2 of the input card. While we're at it, the outputs are actually going to be local, slot 0, O for output, data. So there's the state right there. So remember, only the first 16 count, 0 through 15. The others don't do anything. Everything's a double integer, so even for 16-point card, the first 16 bits only are actually functioning. And then for the inputs, we also want the data word, and the first 16 bits there. So that's what an input address looks like. Local to input data, bit 0 through bit 15. And then, of course, for the outputs, we have local slot 0 outputs data bit 0 through 15. Okay, so now we're going to add a tag into our controller tags, and we'll call it assembly line 1. Okay, and it's an alias for vehicle. Oops. Oh, no, not alias. I'm sorry. I'm not going to start over. I'll just go here to data type. That's what I meant to do. Not an alias, but a data type. No wonder it didn't take the V. Vehicle. I'm going to click. I could click OK, but instead what I'm going to do is make an array of 10. So I killed two birds with one stone here. So I have assembly line 1, car type 0 through 9. So open that up and see type 0. I got type length width blah blah blah. So if I want to edit or monitor, I can look at the values here. So there's type 0, type 1, type 2. See, as I expand them. So once I created that data structure, all I got to do is create a tag for and point it or define it as a vehicle data type. Now just let your imagination run wild with this, because it is really pretty cool. Let me show you one more. I'm going to create one called storage. Okay, this one's a little more complicated because it's not an object that you recognize like a car. And I want to make actually, you know what? I think that I won't make that a user defined. I'm going to do this in another context. Sorry I led you halfway through the door, then backed up and bumped into you there. Sorry about that. What I'm going to do is I'm going to go to controller tags, edit tags, and I'm going to create something called storage. Storage space 01. Okay, and now I'm going to make it an integer. I could make it a string, and actually, you know, a string's probably better because I want to put part numbers in there, and I want to make it 100 by 100 by 10. Okay, you're probably going, now what is this? Failed to create a new tag. The array size exceeds 2 megabytes. Okay, that's because I picked a string data type. So we'll go back and make this a integer. An integer. Okay. Remember, a string, each character can be 8 bits. So depending on what size the string is, I created a 3-dimensional array here of 100 by 100 by 10. So think of 100 foot square on the floor in a warehouse. In other words, on the floor of the warehouse, you lay it out with 100 feet in 2 directions. So you have 1,000 square feet in your square, 100 by 100. Everybody with me? Now, vertically from each of those 1,000 square feet, picture in your mind 10 boxes, each of them 1 foot cubed, stacked up over each of those 1,000 square feet. So you're looking at 10,000 12-inch by 12-inch by 12-inch boxes in stacks of 10, each 10 sitting on 1 square foot in a 100 by 100 square on the floor. That's what you're looking at there, right there. So if you wanted to define that space, in other words, let's say you had different part numbers and you wanted to store them in that space. Now I picked a 100 by 100 feet by 10 feet high. It could just be 100 spaces by 100 spaces, 10 spaces high. So the bottom layer has 1,000 spaces, the second layer up has 1,000 spaces, and so forth. And in between each of the rows of the spaces, you could have a crane type elevator that lifts up boxes or containers or skid loads and places them in any one of these 10,000 spaces. So basically, if you were trying to picture this in your mind, it would be an automated storage and retrieval system where when you look down this warehouse, you see 2 rows of spaces, 10 spaces high, that are back to back, and then in between each 2 you see a rail, like a railroad track, and then on that railroad track there's a lift or crane, if you want to call it that, that travels back and forth, and it can place unit loads, skid loads of parts or product on either side of the rail. So I don't know if you can picture that in your head or not, but in the Logix engine it gives you the capability of 3-dimensional arrays. Very cool. Maybe hard to picture virtually. So let's say that you needed to store 3 designations for each space. You could just go back and edit this one, and we'll call it D1. Then we create another one. See if I can spell it right. Again, it's still 01, but now it's D2. It's the second designation. And then storage space 01 D3. Okay, and then we want to go define these as integers. 100 by 100 by 10. And then you want to do the same thing here. Integer, and you can just type it in if you want to be real clever. Bracket. Oh, didn't like that. So we'll do it this way then. Okay. I did something. Oh. I thought you could just type it in. Sorry about that. Here I am leading you down the garden path. Okay, it just does not like what I did. So I messed it up. There we go. Okay, now I have 3 tag names that are each 3-dimensional arrays. So when you look at the elements, okay, storage space, description or data 1, whatever you designation 1, 0 north, I guess you don't want to do it that way. So I guess it would be, yeah, okay, you could say 0 north, 0 east, bottom level, first level, second level, third level, all the way down, okay, to the 9th level. Then you've got the next square, 10 levels. See, so you have this huge file structure now, and this 000 for D1, scroll down, whoops, scroll down to D2. See, there's 1,000 of them, so you're going to go down a long ways. Anyway, down there, there's going to be a D2 000 as well. So D1 000, D2 000, and D3 000 all are designations or data for whatever's sitting in that one space. Maybe this is kind of hard to picture, but anyway, we had fun doing it anyway. Okay, if you want to create motion, that's a whole other ball game. If you want to create more tasks, you could do that under task, right click, new task. We're not going to do that though. If you've got any motion groups that you don't want in the mix, you can move them to ungrouped axes until you're ready to add them in. Add-on instructions, that's a biggie, but we're not going to cover it in this little lecture. So I think we pretty much have wore this out. So I hope you enjoyed yourself. I hope you learned something. Hopefully this answered 1,000 questions and then created 10,000 more questions about things you didn't know before. That's the general nature of this whole business. So you've got a good jump start now. You can jump in and create your first project with ControlLogix. Thank you for watching.